I think this is the most appropriate time to say to anyone who may concern, because today we're going to show you how we, one of the methods that we used to implement Dickson's paper in 2005 on how to calculate the finite time ruin probability. Well, the title of the paper is the density of time to ruin the classical personal risk model. So the model and the algorithm itself is built on the classical risk model, which your surplus process can be described as your initial capital times the premium rate times time t minus the aggregation of your claims. And we managed to summarize this paper into three equations over here, as you can see. So the WUT is just the density of time to ruin. So if you want to know the if you want to know the finite time ruin probability, let's say at initial capital U and a time capital T, what you need to do is just take the integral from 0 to T, the 0 to capital T to W with respect to this little t over here. So, well, that's all about the algorithm itself. As you can see, when you need to calculate this W, you need C, which is something like this. And when you come to calculate C, you need Bn, which is something like this. Well, that's the algorithm itself. That's all about it. The only problem left to us is how do you calculate it? Because in Dickson's paper, he proposed he gave us an example, but that example is a mixture around claim amounts, which somehow simplifies this problem. But anybody can tell this method works on any continuous function as long as you can find the n-fold. Here n can be any number, any integers. Let's be more accuracy, any integers, n-fold convolutions of this density function. This method will work. So in our implementation, we managed to build a very general code, or whatever, a program, whatever you want to call it, to do the calculation. So the problem we are facing, first of all, as I just mentioned, is whenever you try to calculate the UT or the finite time ruin probability itself, you come across with the integral problem and how we approximate the integral. And the second problem is that you always see this summation to infinity here. And how do you ask the computer to calculate something like a summation to infinity? What is a summation to infinity to a computer? And the third problem is that in order to calculate the single value of W, you need C UCT or C UCT, and in order to calculate each CUT, you need a unique BNUT here. And in order to calculate the BNUT, you need to calculate this equation. So that said, even for a single value of WUT, you need to calculate the C times after time, maybe 100 of times. And for that 100 times of the CUT, you need to calculate BNUT another 100 times. Well, doing all of this could result in a significant amount of time for your computer to do the calculation, which is not practical when you want to make it to use in an actual daily life. Nobody wants to wait hours of hours just for a single value. Never mention it might not even be accurate enough. So the third problem we are facing is how do you make this algorithm works faster and accurate? Well, I can answer the first two questions right now, and for the third question, we need to jump to the code. The first question, how we approximate all of the integrals here. Let's take an example. The integral here from z0 to ct of this thing with respect to y, we just divide 0 to ct into several uniformly distributed intervals and take the value of this inside part at each of these intervals and just summation all of their value and times your interval size is just a rough approximation of the integral. And you may already realize that the more interval size, the more interval that we choose, that is to say, the smaller the interval size we are choosing to using, the more accurate we will be when approximate this integral. And the second problem is about the summation to infinity. Well, the only thing we can expect it here is that this thing, the sequences that you calculated right after the summation sign, is a converged sequences. That's to say, as n increases, the value here decreases. And let's really hope this decreases as quickly as it can be, because when we're doing the calculation, we choose a number here instead of infinity. So we are trying to say summation from 1 to a large enough number here is good enough instead of calculating from 1 to infinity, which I do not believe can be calculated in most of times. So that is the method we choose to solve the first two questions. And for the third question, it's a little tricky because initially when we're trying to implement this method in a very intuitive way, we really ask the computer to calculate each of these values separately. And for each of the W, calculate thousands of Kc, and for each of the Kc, calculate thousands of Bn. And the result is, even on a very high-end my computer, it took about 4 or 5 hours to give us a rough results of ruin probability, which is, of course, something that we can never accept. So instead, I myself spent about another week or so to develop this algorithm or this code I'm about to show you. Now, for very accurate answer, it only took the computer about less than 10 seconds to do so. Okay, let's jump to the, hang on a moment, let's do not worry to jump to the code. Let's see how we're decoding this algorithm. Even for a computer, we still need to calculate this WUT step by step. Let's see. If we want to calculate this WUT, I need Kc. And if I want to calculate Kc, I need Bn. And the elements in Bn are what? You need to take the integral of this capital P and little p. And here, the little p powered by n minus j star means the n minus j fold convolution of little p. And the capital P j star means the CDF of j's code of little p. And that reminds me of something that I see here. You see, if I want to catch WUT, I also need the value of P powered by n star here. And in each of the steps, when I try to calculate the CUT, because you find that one can observe that U is always a constant in all of these three equations. That said, if you ask them to calculate the finite time ruin probability at initial capital U, then that U is fixed. None of the steps here, we are changing the values on U. You see the integral here, we are operating on this t part, which is this t, and you see the integral here, we're also operating on the second part of Bn, the second parameter of Bn, rather than the first parameter, which is the initial capital. And even for this Bn part, we do nothing about U. See, U is always a constant here. So the problems become much more simple than we expected, because instead of considering a two variable two parameter functions, we not only need to consider this one parameter function, another parameter is operating on the time t all the time. And another thing you will come across is that you will notice that it's literally the same calculation again and again when you're trying to find the different values of WUT. So our target is to take the integral of WUT here. So the only variable that is changing is t, and t is going from 0 to capital T, which is increasing or decreasing whatever the sequences you choose. And in order to calculate the WUT with the changing t, the variable that is changing for C is also t. And the same applies to the convolution part here, and the t going from small to large is the same thing asking for Bn of some t going from small to large, and the same thing happens here. So instead of doing the calculation step by step again and again, why don't we calculate the values that we need in each steps of our calculation before we even start off our entire calculation? That is to say, whenever we come across with calculating one of these things, the W or C or Bn, instead of doing the calculation again, we're just seeking the corresponding values from the matrix, the gigantic matrix we built before. I will give you the idea later if I'm not explaining this very, very clearly at this moment. So that is the main method that we employed here to make this calculation faster than the first edition of the program. Okay, now it's time to jump to the code. So we implemented this algorithm into Matlab with functions after functions. So let's try to do this in a very computerized way. The first is the main function, which basically does nothing but claim all of the parameters here. And in order to save memory, we claim all of these shared parameters into global variables. That is to say, all of the sub-functions of this main function can not only visit but also change this parameter. But of course, we do not want them in most of the times changing these parameters. So we have our initial capital, which is U, as you just see here. And we have our lambda, which is a parameter for process, which is a lambda here. And we have our C, which is the premium rate, which also treated as a constant throughout the calculation. And Fx is the density functions, as this what is this little p is. So also we choose the interval times, as I just mentioned before, how we approximate the interval size, how we approximate the integrals, and the smaller the interval size they are, the more accurate we are achieving in approximating each of these integrals. And in our algorithm, we choose the same interval size for all of at least these three integrals we are going to approximate. And the next parameter is n in c and n in omega. Well, as I just mentioned, the second problem we are facing, instead of doing the summation to infinity, we choose a very large number above the summation instead. So here we choose the n in omega. So substitute this infinity to n in omega and substitute this infinity to n in c. And of course, the larger of your n in c and n in omega are, the more accuracy you will achieve in doing all of the calculation. And that's about all the parameters we are going to claim here. One thing about in our particular case, in this particular program, we choose mixture of exponential distribution, just as showing you the example of how this algorithm could work. But it's not only limited to mixture of exponentials, as I will just show you in a moment. And the first row of this fx matrix is the weights of your mixture exponential, and the second is the parameters. In this particular case, we just have an exponential distribution with a parameter 0.75. So if you change this into 0.2 and this is into 0.8, let's do that. And this is going to 0.8 and give another parameter here, let's say 0.5. It means a mixture of two exponential distributions with weights 20% and 80% and the corresponding parameter 0.75 and 0.5. And let me just show you the running of this function. So it took the computer about 6 seconds to do all of the calculation. And well, why the results look so ugly? Well, that's true. And this blue line you see here, this blue line is the finite time Ruin probability. And the x-axis, which I haven't give them labels or to do them or put them in a standardized way. As you can see, our time horizon is 5 instead of 50, so it means times 10 power by minus 1, whatever. So this is our finite time Ruin probability, which is changing throughout time. And this green line is the Basal function results. Basal function results give us the finite time Ruin probability. 1. Your claim is modeled in a single exponential distribution or single exponential density functions. So you can see the huge differences here because instead of a single exponential, we choose a mixture of two exponential here. So if I change them back, you will see something like this. So it took my computer 3 seconds to calculate, doing all of the calculation here. Our results, the blue line, is almost the same as the analytic solution from Basel function, and the red line is just plotting out their differences. So this is just showing you our algorithm really works. And how it works, we have to read the lines step by step. So when we try to run this function, the first function it will run, well, it's of course itself. Then it asks to run the function finite time Ruin, which is defined as the second function here. And the finite Ruin function is basically taking the integrals to this w with respect to t from 0 to the time horizon you are given. And in order to calculate this finite time Ruin probability, a finite time Ruin function, it asks to run the function w function first, and the w function is just the function that we used to calculate this w here. And obviously, in order to calculate this w, the first thing it asks you to do is to calculate this cursive function, which is the function that we're doing the calculation of the cursive. And if we jump to the cursive function, the first thing it asks you to do is to do the Bn function. So you can see the logical here. Step by step, we calculated the w. And this is where we do the most maybe not the most fundamental calculation, but the most fundamental calculation in these three equations, the Bn function. So here are the Bn functions. Let's take a further step. How do we calculate the Bn function? If you look at these equations, you will see Bn function asks you to calculate little p n minus j fold convolution and the capital P. As I just mentioned before, instead of doing all of the calculation in each steps, we are generating all of the parameters, all of the values that we need in our calculation before we really carrying out calculations, these three equations. That said, even below this Bn function, we have a Pn fold function and a convolution function, and the rest are just the density functions that were resulting from fx, the density of your claims. That is what I just said, why our algorithm can work much more generally than the examples that are given by Dickson in his paper, as long as you can tell the computer what is your density functions of your claims. In our example, it's just a mixture of exponential, so I claimed in the way like this, but you can easily change it into any continuous functions that you can write down if you want. So let's jump to the convolution function. In this function, we have two variables. One is max fold, and another is max value. The max fold are just basically saying, so this convolution function, we are trying to calculate the little p here, the n fold. More exactly, specifically is the p's n-fold convolution. So n is ranging from 0 to max fold, which are all integers, and the max value are the parameters following by the p. So after this function being executed or being running, what we generated is a matrix called convolution matrix, and this convolution matrix is at the size from with several rows and columns definitely. Then all of the rows are indicating the values that are going after p, starting from 0 to is the max value here with the step size of our interval size, which we defined in the very beginning of the program. That is to say, the rows of this matrix we are building here are 0 interval size, 2 times of interval size, 3 times of interval size, and carrying on until it goes to the max value that you are putting here. And the clones of this matrix, the global convolution matrix, is from 0 to max fold. So the clones are from 0 and 1 and 2 and 3. So each of the clones are indicating the nth fold of the convolution to our density functions. So let's take an example. The second row and the second clone of this matrix indicate that the two-fold convolution of your density function with the parameter at the interval size, and the third row at the same clone, which is the second clone, would say that the two-fold convolution of your density function at the parameter value at 2 times your interval size. So if you get an idea, then you can understand why our method can make the calculation so quickly, even below, let's say, 4 seconds here. And the good thing about the global variable is once you generated the matrix large enough, you always have this matrix in your RAM, in your memory, in the computer's memory definitely. So whenever you come across with this value, you just take out the value you need instead of calculating them again and again. And basically, the way we're calculating the nth fold convolution is just using the convolution function in Matlab, which you can see here. And the second this is the function calculated the two-fold convolutions. However, the three-fold convolution or four-fold convolution are just literally the same way. If you can see here, we are calculating the two-fold convolution with the convolution with, for example, if you want to calculate the four-fold convolution of little p, the only thing that you need to do is to take the already calculated the three-fold convolution with this function with the density functions of p itself, which is already the one-fold convolution of p. And in the paper, Dickson claims the nth-fold of convolution of little p equals to 1. That is why we are doing this here. And of course, the first row of the matrix of the global matrix convolution matrix is 0, since the upper limit of your convolution or the parameter you are using here is 0. So after finishing the calculation of the convolution matrix, the second thing we're going to do is to calculate the p-n-fold, which is the capital P here. As we just explained, the capital P here is just the CDF of the little p with j-fold convolution. So a very easy cum sum commander will give you the another global matrix, which we call the convolution matrix capital P. And it's almost like the first matrix we built with a maximum fold of columns and maximum value of rows starting from 0 with the steps of interval size. So once we have the p-n-fold matrix, we can calculate the bn function now. As you can see, the bn function is merely just taking, following the way we approximated the integral, it's just merely taking some very fundamental calculations within the capital P and the little p here. And that is the only tricky part. The other part are just a very simple and fundamental calculation, and this summation calculation is not worth to mention about. So how to make this calculation as quickly as we can? And we vectorize it. As if you see deeply enough, to take the integral from 0 to ut, as I just mentioned, we are actually dividing this interval 0 to u into several uniformly distributed intervals with each interval size. As I mentioned here, in our particular case, I do believe is 0.01. And our u, which is the initial capital, is 3. So that said, we have 300 intervals when we approximate this integral. And for each of these integrals, you can find out the value of the corresponding capital P convolution and little p convolution here. And that is and even in here, we can already see the benefit that why we generated these two large, gigantic matrices in front of us, which is called the convolution matrix and the convolution matrix P. This one and this one. Since they are global variables, even before starting calculating the Bn, if you are carefully enough, you can see here, when we're calculating the W function, which is a function here, we already need the convolution of little p. So I initialized this convolution function in the W function. And they already store this global variable convolution matrix in the memory. And when we calculate the Bn part, we still need to know the capital P matrix, which I generated the convolution matrix P in this commander. So For each of the intervals, you need the corresponding values of capital P and little p, and you just taking out them from the corresponding positions in the two matrices you just built, and time them together, which can easily be transformed into a vector time in vector calculation to save you significant amount of time, and times the interval size, as which is modify this dx here, and you get the value of your integral. And doing in this way, we are creating another global matrix, which is called Bn matrix here. Now, Bn matrix is a matrix store all these values that we calculated or that we needed in this in the whole of the calculation. So if you can just take a look, when we try to calculate the finite time Rowing probability till time horizon, let's say capital T, the largest c you need is UC times capital T, right? So if it's larger, if it is c UC times capital T, then you need you have the c times capital T here, and invaluable, and definitely the Bn part is u c times capital T, and in order to calculate the Bn part of the u cap c times capital T, you just put c times capital T here. So the largest matrix you need about the Bn part is from 0 to c times capital T, which I put as maximal T here. So the matrix we are building here is with 0 to max T rows with the interval size which is 0.01 here, and the clones is starting from 1 to n in c. Why n in c? Because whenever it asks you to take the convolutions, you come across with this parameter j and n minus j. However, in the Bn part, this n is fixed by the c. This n is just the summation part in c here. If you still remember, instead of using an infinite sign here, we use n in c as the largest summation part we are going to approximate. So the matrix, the Bn matrix, is with clones from 0 to n in c. So that is all of the Bn values we need in calculating all of these algorithms. Calculate all of these three equations. So Bn c is built also in vectorized calculation to make this running as quickly as it can. So after generating all of the Bn values that we need, we come across, well, we literally finishing the first equations. We do not touch the first equation never again, because all of the values that we need in the following calculation is already generated and stored in the matrix called the Bn matrix, which is a global variable. You can use it everywhere in the rest of your function. So the next part we are going to do, I do believe, is calculated the c function. As you can see, this is the start of the c function. We will already have our Bn matrix here, and the maximal T is claimed just as I said, c times the time horizon. And in order to make our function running much more faster, I built c into a vector, because you see here, when you try to approximate this integral, you are still requiring a lot of c's with different values at different time, y ranging from 0 to ct. So instead of well, it's applying the same idea everywhere. Instead of using the same, instead of calculating C at each of this approximation, why not calculating them out at the first hand? So whenever you come across the approximating integral, you just pull out the values from the vector you already generated. So the C function here is doing exactly the same thing by generating a vector of C with all possible time variables. But the good thing is we've already now the function do not need another input because we already know the largest time variable it could achieve here, which is given by C minus T, right? So following the same way, the same calculation, we build the vector of C array. So after the running of this function, we literally finishing all of the calculations that you need to carry out for the first two equations. So the first two equations are done. We do not need to visit them again, and all of the needed values have already calculated and stored in three gigantic matrices, which are, if we come to the A here, which are the, of course, convolution matrix. Well, if I can remind you again, convolution matrix is just calculating this part, and the convolution matrix with capital P is this part, and the Bn matrix is this part, and the C vector is all of the values we need to in order to calculating W here. So the next step is calculating WUT. So where is it? Okay, it's here. So I initialized the convolution global matrix here because we come across with this value, the p n-fold convolution here and here. But which one is larger? Is t minus u minus x larger or c times t minus y larger? Well, y is ranging from 0 to ct, while this x is ranging from 0 to u, so that is ct here and ut plus u here. Which one is larger? Because our idea is to build this gigantic matrix in front of everything. So whenever you come across with a calculation, you just drag the values that you need here. And that said, you need to build a matrix large enough. Otherwise, you'll come across with a problem. When you need some values, you cannot find the corresponding value within your matrix because your matrix is not large enough. So I built the convolution matrix here with a command of finding which one is larger in terms of n in C or n in omega. Because we have n in C here and n in omega here. Well, to make our program more flexible, I use two different variables for them so that you can approximate your algorithms up with your wish. But I always generated the matrix with the larger one between these two. Because whenever you want to drag the numbers out or drag the values out, you do not, as I just said, you do not want to come across with the situation that you cannot find the corresponding one due to the size of the matrix. So after building the very useful convolution matrix here, then we come to the C function. As I just introduced you, everything follows. We have the vector of C, we have the matrix of Bn, we have the matrix of the convolution matrix capital P, which is used in calculating the Bn matrix. So the rest are fairly easy, I would say. Well, one thing I need to mention here is that when we approximate this integral here, instead of approximating the way that I just proposed, we can approximate another way. If you take a look here, this is actually the definition of convolution itself. If you take cuy and this y as some function of y, and this p n-fold convolution of ct minus y as another function, so this is literally a convolution itself. So instead of using the way I just proposed, I use the convolution way to approximate this integral, which makes this program running more faster. And eventually, I find the value of w at each little t and stored it in a value called, just hang on a minute, in the omega array. As you might already guessed it again, instead of calculating the single value of omega each time, I put it in an array, because the last step we need to do is to take the integral of this omega and find the finite ring probabilities. Nobody want to do the calculation again and again within the integral. The easiest way to do it is to build an array for omega and calculate it just for one time. So with the omega array generated by this w function, we are literally finishing the calculation of all of these three equations. Now, all of the values we need is calculated. The final step is just simply take the integrals. So if I can have a look where we take the integrals, yeah, it's just a cum sum of your omega of our omega area, which is the w value we calculated it out, and times the step size. Because in the last step, when we approximate the last integral, which is the integral to w with respect to t, I choose a different interval size instead of the interval size that we already used throughout the program. The reason to do that is that we do not need too much accuracy in the very last step. Well, if you want, you can do that, but in my experience, we do not need that much accuracy. So instead of choosing a relatively small number, I give it a relatively large number and save us a lot of time in calculation and make our calculation more smoothly. And you can see the finite time ruin is a vector that is the integral from 0 to time horizon of the w we generated here. And in the final step of this function, we implemented the Bessel solution for comparison. As I mentioned in the very beginning of this video, the Bessel function is an analytic solution of finite time ruin with the classical Poisson model on the claims are modeled by exponential distributions. So this is here merely for the comparison to see if our answer is correct or not, So that's about everything. So the main function runs here and asks it to do the finite ruin function, which is here. It generated the value in the blue line and compared with the value from the Bessel solution with the green line and take the differences. So to a conclusion, one can obviously implement this method, as I mentioned before, step by step. That said, in calculate w, you need to c, and calculate c, you need bn, and in order to calculate bn, you need to calculate little p. So for different value of omega or of w, you need to do that all over again. That is the correct way to do this. But in order to make it faster and more accurate, global variance is the elephant in the house here, because whenever you come across the problem like this, you define a global variable here to do the calculation in front of all of the real calculation that you need. And when you come across with the real calculation, you just take the values out of that matrix, will save you a significant amount of time. I don't want to waste time to show you the first edition of our program, which is running 4 or 5 hours, even with a roughly result. Roughly, I mean the n in c and n in omega and n in and interval size I choose. Well, intervals are choose relatively large, while these two ends are choose relatively small in order to accelerate the calculation. But now we can give it more freedom to calculate the much more accurate results. And the whole function works out under 4 seconds, which, well, I do think it's already good enough to implement it in daily life. So that is everything I need to say about the implementation of Dickson's algorithm in Matlab. And we are carrying on much more further analysis on the results that we're achieving and see what is the differences between finite time Rowing probability and infinite time Rowing probability, and what information that we achieved more when take into consideration about this time integral. So thank you very much then.